So my name is Inseung Kang. I'm a PhD candidate in mechanical engineering at Georgia Tech, working at Exoskeleton and Prosthetic Intelligent Controls Lab with Dr. Aaron Young. So mainly my PhD coursework, I've been focusing on developing these robotic hip exoskeletons to really augment humans during locomotions, mainly to provide assistance such that we can really improve mobility, and hopefully we can really translate these technologies to a clinical population such as strokes or elders. But mainly today's talk, I'm going to focus on how do we better provide these assistance that is adaptive to the user state variables. So first, I would like to kind of take a step back and really talk about what is an exoskeleton technology. Mainly, we're talking about these robotic platforms, wearable robotics that can really augment humans for improved mobilities. And in the wearable robotics field, we really segment these exoskeleton technologies into three different categories for their main applications. Mainly, we're talking about human augmentation, where we can really provide assistance to enhance physical capabilities, such as lifting heavy objects or marching for long distance for like soldiers. And then we can think about assisted devices, where we can provide partial assistance during locomotion for people with limited mobilities, such as stroke or elders. And lastly, we can think about rehabilitation aspect, where we can really understand utilizing these exoskeleton system to alter the physical attributes of the user for long-term benefits. So until the mid-2010s, we really haven't seen a lot of huge benefit of using these exoskeleton systems, mainly because we really neglected the importance of human biomechanics and how humans really interact with these robots. So people have started to really investigate and understand the human movement. And starting with the ankle exoskeleton, we've seen that, really understanding the gait biomechanics and really merge both the field of human biomechanics and the robotic controls really start to shine the benefit of using these exoskeleton systems in both active and passive devices. And people really start to expand this knowledge by understanding the human biomechanics and really try to target different lower limb joints, such as the hip joint, and have really recently shown that we're starting to gain really good benefits. And the benefit I'm talking about is reducing the energetic demands or the muscle activation levels and so forth, which we're seeing a lot of good results in both industry and research groups. So this graph kind of illustrates how we've kind of improved over the last decade or so in terms of these exoskeletons. Y-axis kind of illustrate the metabolic cost benefits. Metabolic cost, the energetic demand of the user during locomotion, is considered as a gold standard metric in our field to really evaluate these exoskeleton performance. And these circles and squares on this graph kind of illustrate different literature studies that have shown these exoskeleton performance. And generally, we can see that we're really getting better at this. We're getting better at providing assistance to improve human locomotion. Transforming this kind of graph into more of a milestone graph, we can really see that it's not just about walking anymore. We're starting to see some benefits at different states, such as running, but also different lower limb joint, which is the knee joint. So it's a very exciting time to be around in these exoskeleton field, where we can really see different research groups kind of exploring how to better optimize system profiles and so forth. And these optimal controller of these exoskeletons have been tackled from multiple aspects, such as, how do we provide assistance? Is there an optimal onset timing of assistance? Is there an optimal assistance duration and so forth? And different groups have really tried to investigate and understand the optimality of these exoskeleton assistance levels. And we're seeing some good results. And using these literature informations, people are starting to really develop some more advanced type of controllers where we can really make an assistant profile that is very user specific to further improve the human exoskeleton performance per user basis. But I would like to kind of highlight that there is still a huge limitation of wearable robotics field, and the main gap is that most of these exoskeleton studies that has been done to show these metabolic cost benefits are really limited at a very specific condition, such as walking at a constant walking speed on a treadmill at some condition, which does not really reflect what the humans really exhibit outdoor, where the person might either accelerate, decelerate, go up the ramp or down the stairs dynamically and continuously. So this gap really needs to be kind of bridged between the laboratory setting and the outdoors, which is kind of where we're trying to really tackle these exoskeleton problems. So to answer this research question, we've developed a robotic hip exoskeleton in the lab, mainly an actuator that can provide a system bilaterally at the hip joint, both in the flexion and extension direction. One of the key things that I want to highlight is that we have different robotic sensor suite on the device, such as the joint encoder and the inertial measurement unit, mainly kind of telling you how your limb orientation is in space while you're walking, basically giving you a kinematic information. And these sensor information can be utilized to provide assistance during the gait cycle while someone's walking. So using this robotic platform, how do we actually provide assistance? So we have this controller that we like to call it the biologically inspired torque controller. The idea is that the green graph indicated is the human biological hip moment during gait cycle, so as the person walk in a cyclic manner. And the idea is that we're providing the hip flexion and extension assistance during the region where its corresponding biological hip moment is exhibited. So we can really modulate different control parameters to provide assistance such as the onset timing, the duration, or the magnitude. So how much to assist? How much of an assistance level is somewhat optimal, at least in the metabolic cost sense? And at least in this study, we found out that there is some sort of optimality in terms of energetic return of providing a system magnitude with these exoskeletons, that more is not necessarily the better. There is some sort of optimal levels. In our case, was 20% assistance. And this kind of shows and illustrates the importance of these user state variables, such as, for example, this study was conducted at one constant walking speed. So you can really imagine when you're increasing the walking speed, these biological hip moment will scale relative to the user's walking speed, meaning that the amount of absolute magnitude the exoskeleton needs to assist needs to dynamically modulate depending on the user state variable, such as the walking speed. So we can really kind of tie in these controller has some reliance to these high-level estimation. So let's talk about a little bit the control architecture of these exoskeletons. So we kind of break it down into three-tier control layer where we have high, mid, and low-level layer. Where the high-level layer deals with the user state estimation. These state variables are things called intent recognition. So mainly we're talking about what is the person doing? Is the person going up the stairs or ramp? So talking about the environmental information, but also the gait phase is the amount, how the person is moving in a cyclic manner, and walking speed and ground slope and so forth. And these state variables are trickled down into mid-level layer. Basically, the biologically inspired torque control that I just mentioned will be implemented here, where the control parameter of this controller will be dictated by the user state variable that is estimated at the high level. And we can implement different types of dynamic equations. A common controller that is often used in our field is impedance controller. But mainly in my study, I focus on using these biologically inspired torque controller. And these commanded joint torques will go down into low-level control layer where the conventional robotic control will be implemented, such as the feedback control, to ensure that our desired torque is matched. But for today's talk, I'm going to mainly focus about how do we better estimate the user state variables in a high-level control layer. So let's talk about a little bit more on the user state variables. These variables are not just limited by one variable. It's multiple variables that happens both externally and internally. Internally meaning users' walking speed and the gait phase I just mentioned, but also externally like the ambulation mode as stairs and ramps. So these variables are kind of changes how the human biomechanics, underlying human biomechanics change in a continuous manner. So let's just give an example of slope walking, for example. So if you can really see that as someone walks up the hill and as the incline level gets steeper, you can really see that the human biological hip joint moment, at least in the extension hip moment and the early phase of the gait cycle, really gets increasing in terms of magnitude as the person goes up at a steeper incline. So which kind of shows that these type of state variables are relating to the user's biomechanics, so which we can really leverage these variables to kind of change the amount of assistance level that happens at a mid-level control layer. So now that we've kind of understand that these importance of user state variables, we try to really see, is it feasible? Is it possible to utilize these robotic sensor data from the device to estimate user state variables? And one of the first things that we really kind of try to solve this was the user's gait phase, which is an important parameter that relates to the controlling these exoskeletons. A little bit more explanation about what gait phase is that it's a phase percentage variable that represents the gait cycle. So since the locomotion, walking is a cyclic type of movement where the 0% is the heel contact to the next 100% is another heel contact, you can really represent in terms of percentage. And the importance of these gait phase variable is that these percentage kind of relates to when to provide assistance, so the timing of the assistance. Surprisingly, the conventional way, or the kind of the baseline method that has still been used to estimate these gait phase variable in the field, is using a foot switch marker to kind of really figure out when the event happens in terms of heel contact and compute the average stride duration from previous X number of gait cycle and interpolating the gait phase with in a time-based manner. While this method kind of works in terms of constant walking speed on a treadmill, it really starts to fail when you're trying to translate this technology into technique to overground situation where the person may change the speed dynamically, which can kind of be problematic when you're talking about the mid-level controller being suboptimal in terms of the exoskeleton benefits. So we utilize the sensor fusion-based type of gait phase estimation using different mechanical sensors on the device from IMU and encoders, and have multi-sensor modality where we can train a model that can estimate users' gait phase that is adaptive to dynamic speed changes. So using different hip encoder and the thigh IMU information, we extract out the relevant feature information from these sensors, and we utilize a machine learning approach to estimate the user's gait phase. In our study, we utilize neural network, but we're not limited by this model. We can implement different type of state-of-the-art type of machine learning models and estimate the gait phase, and using these gait phase variable, we can output the relevant system profile in terms of torque space. So this is an example of how robust is the machine learning model to dynamic speed changes. The red graph indicates the time-based estimation, the baseline method, and the blue graph represents our machine learning model estimating the gait phase and the corresponding torque output. As you can see that as the speed dynamically changes by either accelerating or decelerating, you can see that the time-based estimation either lags or leads the estimation, causing some suboptimal performance in the torque output, whereas our machine learning model can dynamically adapt to these speed changes. So these bar graph kind of represents our main findings, where the red bar basically tells you about the time-based estimation, our baseline, and the yellow, green, and blue bar graph indicates the machine learning model leveraging different user data sets. So IND, the independent model, or the DEP, the dependent model, is basically a model that utilizes generic pool of independent subject and testing on a novel user, versus dependent model is the model that is trained specifically on the testing subject. The interesting thing that we've really found is that machine learning model, while the performance is very similar in terms of baseline time-based estimation, it really starts to outperform this baseline model when it's dynamic type of speed changes. Additionally, the one thing that we really found is that this semi, which is the semi-dependent, it's the intermediate between the independent and dependent model. So you start with a generic independent model and really have a user-specific data in a small batch to train this model to really outperform in estimating the user's gait phase, where we can really start to see the idea of these transfer learning, meta learning type of paradigm, where we can leverage the user-specific data in a small subset and really improve the user-independent model. So we're getting pretty good at estimating the internal state of the user. Now we really wanted to kind of figure out, can we do some environmental information estimation? So one of the key parameter that is really important for exoskeleton controller is the locomotion mode as the person navigate through different terrains. One of the equipments that we have in the lab that is a train part. It has an adjustable height capability where we can emulate different type of scenarios of different stair heights and ramp inclines that can mimic the outdoor environments, and we can really test the these mode classification, I would say user intent recognition using these exoskeleton systems. Similar paradigm where we use different robotic sensor from the exoskeleton to estimate these locomotion modes. One of the key things that is really important, the reason why this type of mode classification is really important is that, as you can see, this is an example of someone going down the ramp. You can see that even just as simple as the hip encoder angle value are changing at a different modes. And we can see that from a biomechanics perspective, the level ground versus ramp descent locomotion has a complete different biomechanics, meaning that a system profile should be different. So the key idea indicated by the blue section is the transitional gait cycle. The idea is that this intent recognition system should be able to predict the person is about to go to this next mode in a fast manner such that we can really switch the mid-level controller correspondingly to the next mode so that we can provide a system that is seamless and natural to the user. So this is a pipeline that we've set up for doing a continuous locomotion classification. So in order to do that, similar to the gate phase, we extract out some sensor information such as the encoder and IMU, and then we implemented different type of machine learning models. In this case, we've implemented something very is a standard, it's called linear discriminant analysis method, but we can implement a different type of machine learning model approach as well, such as neural network in this section. But also, I'd like to add another layer of filtering techniques. So the idea is, while the transitional gait cycle is important, also the steady state estimation of these classifications. So while the person is going up the ramp or staying in that state, can we ensure that there is no switching back and forth between the state? So we add a filtering technique, and at least in the classification sense, we add Bayesian network to really improve the steady state error. In a regression sense, we will probably implement a common filtering type of approach. So this results kind of shows that left showing the transitional gait cycle error using our method versus the steady state error on the right. And the red, green, and blue graph kind of indicates the complexity of these LDA, naive Bayes, LDA, and QDA. So we're trying to increase the complexity of implemented model. And where we can see the transitional gait cycle wise, increasing the more complex model did improve in correctly classifying the transition to the next mode. But interestingly, one of the key things that we found is that at least on a steady state error sense, increasing complexity does not really yield better results. And this may be due to multiple reasons. One of the good examples is the curse of dimensionality, where we have too many features to train these QDAs. But the idea is that, interesting idea is that there is still some sort of optimality in terms of high-level type of model, which is very consistent with the mid-level type of studies, where not complex or not more is always the better. So where do we move from these type of studies? Is that as shown in the gate phase study, now we're trying to really tackle this by improving the model accuracy furthermore by implementing some transfer learning paradigms. The first thing that we really wanted to kind of tackle is, can we make the baseline model improve further? So in our previous study in the gate phase estimation, we utilized the regular feed-forward neural network, which is shown in the orange bar, and then we're trying to really implement different type of more advanced type of neural network models, such as the convolution neural network or LSTM recurrent neural network. And really we've made the baseline to even perform better in terms of at least the user independent type of models. And then using this baseline model, we really try to leverage the semi-dependent type of paradigm I just mentioned previously, where we can really implement an adaptation paradigm where we start with the user independent model, but as time progresses and the users start to use these exoskeleton, we extract out additional sensor data and then really adapt these models to be semi-dependent on the fly. So the idea is that you can see that the red graph shows the independent model, so it really doesn't change the model accuracy even the time progresses, but you can see on the blue graph where the error rates start to decay because we're start to train the model and update the model such that over 2 minutes and 44 minutes of usage of these exoskeleton, this exoskeleton gait phase estimation at least, the model will start to adapt to the user-specific type of gait parameters. So we've just kind of finished these offline studies, and over the summer, we've actually collected these online adaptation strategy, so the adapting these model in real time to see really, is it feasible to really use these online adaptation paradigms in real time to control these exoskeletons. So what we've done is that we've trained these offline models that is user independent. For example, training a model that is based on 10 subject data and try to test it on the 11th subject, which is a novel user. And the idea is that real-time implementation of these adaptation is that we're basically, as the person walks with this device, we're trying to predict the gait phase in real time, but in a slower sense, in a pseudo real-time manner, we'll collect the data, label the user's gait phase, or in this study, we did a walking speed estimation as well, and backward estimate and update the model on the fly. So basically, can we have the subject over time really outperform these gait phase estimation using these online adaptation paradigm? So what is the future direction of my study is that now that we've kind of made different bits of high-level estimation models, we really want to kind of merge everything together to continuously modulate the exoskeleton assistance in a dynamic setting, such as different incline levels, modes, and walking speed, and so forth. And really try to tackle more understanding of meta and multitask learning, where we can leverage these transfer learning paradigms to adapt the model to the user-specific basis. And lastly, we want to translate these techniques to a clinical population where we can really see the huge benefit of implementing machine learning models, such as on stroke survivors. And these are my funding source, and now I'd like to take questions. Thank you.